As we continue our discussion of solubility equilibria, we will be asked to answer questions like this. If 20 milliliters of 0.1 molar barium nitrate are added to 50 milliliters of 0.1 molar sodium carbonate, will a precipitation occur? Well, when we hear will a precipitation occur, we think QSP officially, and we're going to need to compare Q to KSP to see if a precipitation will happen. I guess I should first point out that when barium nitrate is dissolved into solution, is it soluble or insoluble? Soluble, so it splits completely into a Ba2 plus and an NO3 and two NO3 minuses. All nitrates are soluble. There are no exceptions to nitrate solubility stuff. Sodium carbonate, also a soluble compound. Sodium is an alkali metal, and all alkali metals are soluble. There are no exceptions to the alkali metal solubilities. So absolutely, things will dissociate like so. All alkali metals are soluble, all nitrates are soluble. So that actually leaves barium and carbonate in solution together to potentially hook up and make a precipitate. So we're going to have a solution of barium and nitrate. That's a 3. And we're going to add it to a solution of sodium and carbonate. And the question is, do we get some barium carbonate sinking to the bottom or not? There's still going to be nitrate and sodium floating around in solution, absolutely. So do we get barium carbonate sinking or not? Yes, barium carbonate comes together and makes an insoluble salt. However, we need to know if the concentration of barium and carbonate are above the threshold for this precipitate to happen, for the precipitation to occur. Okay. When you put these things in solution together, the barium starts out at 0.1 molar, but it's 0.1 molar in this small volume of 20 milliliters. It's not going to be 0.1 molar when you put it in the beaker that's now containing 70 milliliters of stuff. That barium will be diluted. And maybe that's a buzzword that you remember the dilution equation from before. M1V1, oh, that's a V. M1V1 equals M2V2, dilution equation. You can think of it that way. Because it's a ratio type thing, we can say it's 0.1 molar barium times 20 milliliters. It's the one and only time, one of the very few times, we don't have to convert to liters because it's a ratio. 2 plus. Why is my hand disobeying? 2 plus. And my total volume now is 70 milliliters. Plug and chug, and I figure out that my concentration of barium in the new 70 milliliter solution is 0.0286, if I did my math correctly. Let's hope I did. That's my new concentration of barium. Okay. What about my new concentration of carbonate? That's the other ion that I care about in this precipitation thing. It starts out as 0.1 molar in a 50 milliliter sample, and it gets diluted to 70 milliliters also. And I get a concentration of carbonate that's now 0.0714 molar. Now what? The reason we're comparing these is because we've identified barium carbonate is an insoluble solid, and so we treat it as an equilibrium type thing. To make aqueous ions of barium, breaking down into aqueous ions of barium and aqueous ions of carbonate, this is a KSP equation. And so this is what we have in mind when we're calculating our Q and our K. So KSP expression would be barium concentration times carbonate concentration. So that's why I did the calculation to find barium and carbonate's concentration. So QSP is equal to 0.0286. That's barium. times 0.0714. That's carbonate. QSP is 0.00204. Okay, I need to compare Q and KSP. KSP I look up in a table because there is lots and lots and lots and lots and lots of KSPs in tables. 8.1 times 10 to the negative 9 is the KSP of this guy. Q is much greater than K. Since Q is greater than K, we say, does it precipitate form? Yes, absolutely precipitate forms because we've got Q greater than K. Okay, knowing all of that work was to find out, does a precipitate form? If a precipitate forms, it does. Determine the concentration, or mass if it's a solid, of all species present at equilibrium. Okay, what now? So we've confirmed that a precipitate will happen, but how much stuff precipitates? We're going to do a limiting reactant thing to determine how much precipitates. And the limiting reactant thing is going to be a limiting reactant table, because I really like those. Limiting reactant tables have start and end numbers, and they give me mole units of start and end things. These things are going to come together to make a precipitate. And we talked about in one of the recent videos that this is considered a limiting reactant when it's forward and forward only. There's enough stuff to come together to make some precipitate. So we put mole numbers in here. Our moles of barium would be 20 milliliters and 0.1 molar. Using that information, 0.02 liters times 0.1 moles of barium per liter gives me 0.002 moles of barium present. 0.002 moles of barium present. Same calculation, but using carbonates numbers. We got 0.05 liters, because it was 50 milliliters. 0.1 moles of carbonate per 1 liter. So that gives me 0.005 moles of carbonate. I should say it's officially proper to do the whole conversion this way. It's 0.1 moles of sodium carbonate per 1 liter. And for every 1 mole of sodium carbonate, you get 1 mole of carbonate. But I knew that my ratio was 1:1, so I went ahead and made the assumption that it's 0.1 molar carbonate, just like it's 0.2 molar sodium in that initial solution. Okay, so 0.005 moles of carbonate. No barium carbonate has happened at the beginning, has precipitated at the initial start of this reaction. I'm going to change some in the middle. I'm going to lose some of this, and gain some of that. And it's 1:1 for everybody. The way you solve for X in a limiting reactant table is set your reactants equal to 0 and solve for X. Well, these are really simple ones because they're both a coefficient of 1. But we'll walk through the method anyway because it's officially how it's supposed to work. Set both reactants equal to 0 and solve for X. The smaller X value is your limiting reactant. So that means X really equals 0.002. So we have 0 barium left. We've got 0.003 moles of carbonate left. And we have created 0.002 moles of barium carbonate. Now what? Well, we're told the concentration of everything at equilibrium is what we want to do. This is not an equilibrium table. This is a limiting reactant table. This tells us the instant you pour those two solutions together, a precipitation starts to happen, and we create some barium carbonate as this precipitation happens. And as the reaction is happening, we deplete all of the barium 2+ in solution. However, for a reaction to be at equilibrium, no concentration of an equilibrium process can be equal to 0. That was a weird way to say that. But so at the end of our limiting reactant table, it says we've got no moles of barium left. But that's false. The precipitation has happened and it has consumed all of the barium 2+ in solution. However, this starts to establish equilibrium after you consume all the barium, and some of the barium carbonate that has precipitated now starts to dissociate. Is it dissociating a lot? Absolutely not. It's only dissociating a little tiny amount because barium carbonate is an insoluble solid, but it is not possible for something to be equal to 0 in an equilibrium process. That's not a thing. So barium, even though the end of our limiting reactant table said it was 0, it cannot stay that way and be considered at equilibrium. So I take my equation from my precipitation and I flip it around backwards to show the new dissociation of the solid that I made. And I'm going to make a rice table, an equilibrium table this time, to determine how much of everything is present. Okay. So rice tables have molar numbers in them. Limiting reactant tables have mole numbers in them. Barium carbonate is a solid. We really don't care how much is there, but we're going to do some more with that. The end of our limiting reactant table says there's 0 moles of barium, so 0 moles over any sort of volume, still going to be 0 molar. The ending row of our limiting reactant table said I've got 3 moles, 0.003 moles of carbonate. So we'll stick it on this page here, 0.003 moles of carbonate. It's now a 70 milliliter solution, so that's 0.07 liters. My carbonate, the beginning row of my equilibrium table, ice table, rice table, is 0.043 molar carbonate. Or 3. It's not 0 because I really do have some already present in the beginning. But I'm going to lose some barium carbonate because it starts to dissociate a little tiny amount to produce some barium because the concentration of barium cannot be equal to 0. Okay, how do we solve to see what x actually equals? In an equilibrium table, you solve for x using your KSP, QSP, KC, KP, that kind of expression. We'll just rewrite it one more time for your viewing pleasure. I almost made that a 2+. Yikes. 2-. So we know from looking it up in the table that KSP for this guy is 8.1 times 10 to the negative 9. Barium is x. Carbonate is 0.043 plus x. And then we get to do something cool. Something that we haven't had a chance to talk about much thus far, but we get to do something cool. If KSP, if K is small, this K is small, right? Would you agree this K is small? If K is small, it's going to mean there's very little product in solution. Remember, when K is small, it means you have very little products. It means reactants are favored at equilibrium. So when K is small, it's going to mean that X is small. And when K is small and X is small, you can do something fancy sometimes. If X is something tiny like, let's say, 1 times 10 to the negative 5th, would adding 1 times 10 to the negative 5th to 0.043 change 0.043 significantly? No, it would make it 0.004301. That's not a significant change. So when you add or subtract a very tiny x from a number that's not super tiny, it's not going to affect that number very much whatsoever. So we get to say, let's pretend that this x doesn't exist. I do not get to ignore that x, but the one that's added or subtracted from the other number, I get to ignore. And if I ignore that x, it allows me to solve this equation without having to do a quadratic equation. Woo! I'm real grateful to not have to do the quadratic equation. So if I solve for that x, just dividing 8.1 times 10 to the negative ninth by 0.043, I get x equals 1.88 times 10 to the negative 7. If you really feel like you want to, you can do the quadratic equation on this guy and see how close your x is using the quadratic equation versus the assumed x is small kind of thing. We're going to say this approximation is always x is small. We don't care. So, if I fill in everything, my concentration of barium at equilibrium is now x. 1.88 times 10 to the negative 7. That's that number. My concentration of carbonate is officially 0.043 plus 1.88 times 10 to the negative 7. That's still going to round to 0.043. I should put molar because units. We care about units. Units. It says the concentration of everything. There's also some nitrate in solution and some sodium in solution. If I click backwards a little bit, nitrate and sodium, well, if barium was 0.0286, it means that nitrate was 2 times that in my initial solution, because for every 1 barium nitrate that dissociates, you get 1 barium, 2 nitrates. So 2 times barium is going to equal the concentration of nitrate. Did you follow along on my super crowded slide right here? 2 times the concentration of 2 times concentration of barium in my dilute solution will equal the concentration of nitrate. So many clicks. So that gives me a nitrate of 0.0572. Because nitrate is a spectator, we don't have to do any kind of reaction with a nitrate. And sodium is exactly the same as carbonate. You do with sodium the same thing you did with nitrate, in that sodium is 2 times the concentration of carbonate, the initial diluted concentration of carbonate. I'm saying this one right here. 2 times carbonate equals the concentration of sodium. Again, because sodium is a spectator, it does not react. So I do my 2 times that, and I get back to where I'm at. There we go. 0.1428 molar. I could write out all the stuff of how I got there. And the very last thing, they want to know the mass of the compound if it's a solid. So how many grams of barium carbonate did we make? Oh boy. I'm going to click backwards for this one and maybe I can squeeze in some work somewhere. We made 0.002 moles of barium carbonate solid. So we need to find out how many grams of barium carbonate solid that is, and I'm going to squeeze it where I've got a little bit of room up here. 0.002 moles of barium carbonate times 1 mole weighs how many grams of barium carbonate? What do we need to find? The molar mass? Molar mass that I calculated, 197.33, I do believe. And that gives me a mass of 0.395 grams barium carbonate. 0.395 grams. That was one problem, and it took us a really long time to work through it. A precipitation problem, you first do Q calculation to see if Q is greater than K, that a precipitate forms. Well, actually, even before that, I should say. You first identify what your precipitate would be. You identify what your insoluble salt would be. Then you calculate new dilute concentrations. Then you calculate Q and compare it to K. And if Q is greater than K, yes, you get a precipitate. Then you do a limiting reactant table to figure out how many moles of everything you make and what runs out first at the end of your limiting reactant table. But because something officially runs out at the end of your limiting reactant table, that's not the end. You have to determine the equilibrium concentrations because something cannot be equal to 0 and be at equilibrium. So you do an equilibrium table after your limiting reactant table to get the concentration of everything. We got to take a tiny shortcut to not have to do the quadratic equation and assume x is small because our k was small. And then we did a final mass calculation, and here we are. Whew. Precipitation problems. They're a lot of work, but I believe you can do them. Couple of things and then we're done. How do you know when you need to do a limiting reactant table? If you have a large K value, if you look back at the limiting reactant table without me having to click backwards, the limiting reactant table that we did was the reverse of the KSP equation. So it means the value of K for our limiting reactant table that we did would be 1 over 8.1 times 10 to the negative 9. And 1 over 8.1 times 10 to the negative 9, that's a really large number. So that's how we knew we needed to do limiting reactant. Okay. Often designated as large when K is greater than 10 squared. So, yeah, large. What does a large K actually mean? It means mostly products, products. It means the reaction essentially goes to completion and there are very little reactants left over. Okay. We do limiting reactant tables when there's, quote, a real reaction taking place. So far, this means precipitation. We're going to do some other types of calculations where we do limiting reactant tables, but so far it's just a precipitation. Ions coming together to make a solid. What types of numbers go in a limiting reactant table? Moles. It is not molarity, it is not grams, it is moles in a limiting reactant table. A rice table, an equilibrium table. How do you know when to use one of those? When your K value is small. If you have a tiny, small K value, use a rice table. It's designated as small when it's 10 to the negative 2. Okay. Small K actually means mostly reactants. There's a little bit of product present, but mostly reactants. We use rice tables when a real reaction is not taking place. What the heck do I even mean? In this specific example, that was meaning that we had some barium carbonate sitting at the bottom of our beaker. And that barium carbonate, a little bit, was dissociating into solution. That's what I would not consider a real reaction. It's just a little bit dissociating. Okay. So far, this means an insoluble compound being dissolved in water and the slight production of ions in solution. Apparently, I said it in fancier words when I wrote it down originally. What kind of numbers go in a rice table? Molarity. Concentration values go in there. That's the end. Whew. Goodbye.